This is a video on ionic bonding. This is part 4 in a series, and our last video on ionic bonding. It has to do with the particle structure, or small size structure, and the macro structure, or large scale structure, of both ionic compounds and metals, as well as the properties that we observe as a result of the structure of the compounds. Now, metals are involved in this unit, not because metals are ionic compounds, but it's pretty traditional to study metals right after you study ionic compounds, so we'll include them in this unit. At the end of this video, you should be able to answer these 10 questions. Number 1A, what is the definition of electronegativity? Number 1B, which have higher electronegativity, metals or nonmetals? Number 2, why are ionic compounds brittle or not malleable? Number 3, why do ionic compounds have a high melting point? Number 4, why do ionic compounds only conduct electricity when either dissolved or melted? And number 5, give an example of an ionic compound you use every day. Number 6, list the 4 properties of metals. Number 7, give an example of how a metal is malleable. Number 8, give an example of how a metal is ductile. Number 9, what happens to the dull, rough surface of a metal when you polish it to a shine or luster? And number 10, what theory explains the 4 properties of metals? Now, before we go any further, we should review electronegativity that we covered in a previous unit. Electronegativity is a calculated value. It was invented in 1950 or thereabouts, and it's defined as the attraction that an atom has for bonding electrons. Once again, this has to be calculated. This can't be observed directly. But we notice that when we calculate these values for the elements, that metals, which are the elements to the left of this zigzag line, generally have low electronegativity, and nonmetals, which are to the right of that zigzag line, generally have higher electronegativity. So we see increasing electronegativity in general as we go up and to the right on the periodic table. That means that if you have a metal combining with a metal, we have 2 elements that are both with low attraction for their bonding electrons. That is the bonding electrons or valence electrons around an atom's own nucleus, as well as the valence electrons around another atom's nucleus. And if they're not pulling on the valence electrons very tightly, what they end up doing is passing those valence electrons readily back and forth between the 2 metal atoms. And the result is a metallic bond. That's explained by the sea of valence electrons model, or sea of valence electrons theory. We'll take a look at that in a little bit. If you have a metal with low electronegativity, low attraction for bonding electrons, bonding with a nonmetal, high electronegativity, high attraction for bonding electrons, we get an ionic bond. The metal loses electrons to form a positive ion. The nonmetal gains those same electrons, forms a negative ion, and we know opposites attract, so these ions stick together and form an ionic compound. In a macro scale, we see a crystal formed that's made of ions. Now, we're not going to take a look at this in this video or in this unit, but the other type of attraction that can happen is when 2 nonmetals are attracted to each other. That's when they're both pulling a lot on the bonding electrons, and as a result of that, they share the bonding electrons. They both have high electronegativity. So covalent bonding is the name that we give for that. They're cooperating and sharing the valence electrons. The result of that in a particle scale is a molecule. Cula mole means little lump in Latin, and the macro scale version of that takes on many different forms. We'll take a look at that again when we get to our chapter on covalent bonding coming up. For right now, let's focus on ionic compounds. Ionic bonding is when ions are held together with ionic bonds, the strongest type of attachment that can hold particles together. An example here is an example of a sodium chloride crystal that's made of sodium chloride ions. Now, this is the strongest bond because not only the negative ions, but the positive ions as well all have octets. That makes them very stable, so they're going to be stuck in place the way they are. And notice that they're bonded on all sides, front, back, left, right, top, bottom. Now, crystals can have all different structures because sodium chloride is made of ions of sodium and chlorine that have similar charges, 1 plus and 1 minus, and size of ions. We get a nice, evenly structured crystal there that takes a cubic shape. Now, sodium chloride is not always going to be perfectly cubic. If you break a little corner off, for example, it might not be a perfect cube, but we would call that an irregular crystal in that sense. Notice the chemical formula NaCl, or Na1Cl1 if you want to put the ones in the formula. That can have two different interpretations. You can look at that as a formula unit, which would be the smallest piece of a sodium chloride. If we had only one sodium and one chloride, we would call that a formula unit. If it were a covalently bonded compound, the smallest piece would be called a molecule. And the word molecule is very often used generically, even when we're talking about formula units for ionic compounds, so just be aware of that. Technically, formula unit is the correct version, or the correct term when you're talking about the smallest piece of an ionic compound, and molecule would be the smallest piece of a covalently bonded compound. You can also look at this chemical formula and interpret it as a crystal, made of any number of ions as long as they exist in a ratio of 1:1 for sodium chloride. Now, the chemical formula for different compounds would give you different ratios, but in this compound it's a 1:1 ratio. So you could have billions upon billions as long as the number of sodiums and chlorides were equal. So a crystal is a regular repeating pattern of particles in general, and in this case we're looking at a crystal of ions. But it doesn't necessarily have to be made of ions. Here we have some sodium chloride that I just got at the grocery store, but here's some sucrose or table sugar that I also got at the grocery store. And the crystals of sugar are not made of ions, they're made of molecules, very much like if you were to freeze some water molecules into an ice cube or into a snowflake, you would see that you have crystallized molecules of water. So crystals don't have to be just ions. And we'll take a look at how crystals of molecules behave when we take a look at covalent bonding later on. For right now, again, let's focus on ionic compounds. And you can see ionic compounds have four properties in a macroscopic scale that result from the way that these ions are bonded together. So on a large scale, we see that solid crystals form at room temperature for ionic compounds, and they have high melting point, or MP. That's because multiple strong bonds exist to hold these ions in place. Again, take a look at that chloride. It's bonded to an Na1+ above it, below it, to the left, to the right, to the back, and to the front. So in all directions, it's locked in place. Makes it a solid, makes it have a crystal structure or a repeating structure, and it makes it very difficult to melt it. You really have to get the temperature high. Remember that when particles are solid, they vibrate in place as their motion. So if you get it to vibrate more and more and more as you're heating this particle up, or heating the substance up, eventually the particles will vibrate so much that they do break apart from this structure that's holding them together, and then it would melt and become a liquid. But with ionic compounds, we're talking about temperatures approaching the temperature of lava. In fact, lava is made of liquefied ionic compounds. So if you were going to try to melt some sodium chloride in your house, you'd burn your house down, melt your stove, melt the pot. You couldn't do it. It's too high of a temperature. Now, what if you did break this crystal structure apart? What if you got it so hot that you did melt it? There are some industrial processes. For example, in the making of glass, we sometimes use some molten or liquefied ionic compounds. Well, in that case, they would conduct electricity because that means the ions could flow or move around. And when ions are free to move around, and that happens both when it's melted and when this compound would be dissolved, then that allows for the free flow of charge or the flow of electricity. So dissolving means that you use a solvent to pull apart the crystal into individual ions. Now, not all ionic compounds can be dissolved. If you take some sand and put it into a bucket of water, it's not going to dissolve. But if you put some sodium chloride in some water, it will dissolve. So the fact that it conducts electricity depends on its solubility, whether it can or cannot dissolve. Let's take a look at the properties of ionic compounds before we move on. One of the properties is that they're solid crystals at room temperature. Let's consider a crystal of sodium chloride. And I'm just going to look at the very face of the crystal here. And what we see is a sodium bonded to a chloride, bonded to a sodium ion, and so on. And there would be these attractive forces. I have them written down in light blue there, where the chloride and the sodium are pulling on each other and holding each other together in that crystal. Remember, opposites attract. That's the law of electrostatics. Now let's say that we take a hammer or some other force and we hit the crystal and we force these ions downward so that now they look like this. what happens is the sodium and the sodium that are both positive come into contact, and now they repel. Remember, opposites attract, likes repel. So the chloride and the chloride would also repel, and the crystal would break apart into pieces. Let's take a look at an example of that with some sodium chloride. So I have some sodium chloride here that I got from the store. This is just regular granules of table salt, and I'm just going to use a black background here so we can see a little better. And we can see the granules are relatively large compared to another version of salt that I got at the store. This is popcorn salt. And typically when people put popcorn on their, or salt on their popcorn, they want that salt to be nice and finely divided up. And you can notice the popcorn salt grains are much more finely broken apart. If you were to try to put any kind of force on these, you could continue to break those grains up into smaller and smaller and smaller pieces. The grains of table salt are bigger than the grains of popcorn salt. Let's take a look at conductivity. To do this, I made what's called a conductivity apparatus. And what this is a light socket and a little light bulb in there. And it's a pretty low wattage light bulb, so it'll be easy to light it up. And I have electricity coming into, typically in a wiring system, the electricity comes in on the black wire, that's the hot wire. And if we follow that through, we can see that wire goes to this plug. When you have a polarized plug like this, the small end plug, the thinner plug, is where the electricity is coming in from an outlet in the United States. So we see that small end's going up this wire into the light bulb, and it's coming out this wire, and it's going to this bare wire here. And then the other side, if that wire is connected, will go to the other side of the plug. It goes to that bare wire there. So if I were to strand these wires together and plug this in, what we're going to see, and I'm going to be careful not to touch that because that would give you a bad shock. What we're going to see is the light goes on. So let me unplug that again. And take those wires apart. Just going to get them under control there a little bit. And let's go ahead and plug this in, and I'm going to keep these wires separated. And I'm going to be very careful not to touch these wires. This is actually a relatively dangerous operation because we're dealing with live electricity here coming in from an outlet. So if I were to take some tap water, and I have some tap water right here. Now people say water's conductive, and that's true if you have tap water. If I put these electrodes, these two wires, into the tap water, and by the way, we do have live electricity there. Notice how bright the light gets when I touch the wires directly together. Notice that when I put them in tap water, the light only gets somewhat bright. If I touch them together while they're underwater, the light gets brighter. So tap water has some electrolytes in it. It has some ions that are dissolved. Let's take a look at this same setup where I'm using some distilled water. Distilled water is an example of water that's been deionized. So ions are typically non-volatile. They don't evaporate. So if we go through the distilling process, we can separate out the pure water and leave the ions behind. Now this is pure water, all molecules, and molecules don't have charges. So when I put these two wires, and again these are live wires so they'd light up the light, into the distilled water, it does not light up. Now just to show you that I'm not pulling a fast one here, let's go ahead and put some sodium chloride ions in that water. Look at that, it lights up. And in fact, as I mix it up, it lights up pretty consistently. Now, what would happen if we were to take a substance and mix it in the water that's also made of molecules like sugar? So let's put some water in there. And let's get that table sugar. Put some sugar in that water and mix that up. Again, live wires. Mix that up. Make sure that sugar is well dissolved. And notice that no matter how much that sugar dissolves, it does not conduct electricity, because when the sugar goes into the solution and becomes dissolved, we see molecules that are dissolved. If I touch those wires together, the bulb lights up, but when I separate them, the bulb does not light up. Now, we could also use a solution that has ions dissolved in it, and we typically would call that an electrolyte solution that's commercially produced. Here's an example. This is some Gatorade. So if I open that up and I put this in there, now the commercial says you got to get your electrolytes, and sure enough, there are electrolytes in that Gatorade, right? We'll put one wire in, put another wire in, there we go, conductivity. Turns out that your nervous system operates with electricity, and we need electrolytes in our body so that we have conductivity from one nerve to another. And you know what happens if you don't have enough electrolytes? Your muscles cramp up because your nerves are not firing appropriately. So sodium chloride is an example of an everyday compound that is an ionic compound. And of course, water and sugar are molecular compounds. They're covalently bonded. We'll take a look at those in the next unit. Let's wrap this up by taking a look at metals now. So metals are not ionic compounds. Metals are held together by what's called metallic bonding. Remember that metals are from the lower left-hand corner of the periodic table. They have low electronegativity. That means they have low attraction for bonding electrons. Metals essentially are playing hot potato with their valence electrons. The result of that is not necessarily a chemical bond. It can be, depending on the crystal structure. If you take two different metals and you combine them, and we get a crystal that repeats throughout the material, we would say that is an intermolecular compound. But if you take two metals and mix them together, and we don't get any repetitive crystal structure that forms throughout the material, we would consider that to be more of a mixture or a solution of metals, and then that would solidify once you cool it off, and that would be referred to as an alloy. So we could get both an alloy or an intermolecular an intermetallic compound from the combining of metals in this metallic bonding. Now you could have metallic bonding happening if you have a pure metal too, like if you have a solid chunk of gold or a piece of silver or a piece of iron. We would see metallic bonding happening there as well. So here's what happens with the sea of valence electrons. The bonding electrons, the valence electrons, are being passed back and forth between the atoms, and that results in the atoms having a positive charge. So I have circles around these positively charged atoms. And now imagine these electrons are moving around there. If you've ever gone to a pier or a dock and stepped onto a boat that's tied up to the dock, you know that you have to be careful because the boat will move, because the water will move. So because these electrons are moving, it allows the positive ions to move within the material. So we get as a result, we get these properties of metals. Number one, metals are malleable. That means that they can be bended or shaped if you put a compressive force on them. In other words, if you press on them or pound them, you can get them to change their shape. They'll bend. Metals can also be ductile, or that means they're stretchable. Like bubble gum or silly putty or slime, if you pull on it, it'll stretch out. It also has to do with the fact, all of these properties have to do with the fact that the atoms can slide around each other as the electrons are moving around. They allow for the atoms to move around. The electrons kind of act like a lubricant between those positively charged metal atoms here. You can shine the metal out. You can take the surface and smooth it out. Now, if you have an irregular surface, and that would be like, say, a surface on this cover, here. There might be a little bit of repulsion, or if you look on this pen, or, sorry, a little bit of reflection of light, but the light is not reflecting perfectly. We have an irregular surface, and as the light hits the surface, it bounces off in all directions. But if you have a flat surface, when the light hits the surface, it bounces off in the same direction. So this is called the diffuse reflection. That's what you see off substances that don't give you a perfectly shiny surface. This is a regular reflection. That would be like a mirror reflection. And that only happens when you can smooth the surface out and make it shiny. So if you take a abrasive cloth or an abrasive compound and you push down on the metal, you can smooth out the surface and make it flat. That makes it shiny. And then finally, metals are conductors. If you push an electron onto a wire, it'll bump all these electrons into each other, and another electron will come bumping off the other end of the wire. Now, a little bit of the energy will be lost there. We call that electrical resistance. But the energy of this electron transfers somewhat to the energy of the electron coming off the other end. If you push this electron with a lot of force, we get that electron coming out with a lot of force. That's voltage. If you push a lot of electrons, we get a lot of electrons coming out. That's amperage. And again, the resistance to the transfer of electrons like that is called resistance. So let's take a look at these properties, and they're all explained again by the sea of valence electrons theory. That metal atoms have a low electronegativity, so the electrons are moving around, the valence electrons are moving around readily between the atoms. And when metal atoms are grouped together with other metal atoms, whether they're the same element or different elements, and they could be alloys or intermolecular compounds, they transfer their valence electrons back and forth so much that they create a sea of valence electrons. The metal atoms become cations or positive ions because of their valence electrons are being delocalized or not stuck on them. They're not fixed in one place. The metal cations are free to flow in the sea of valence electrons because the moving valence electrons act as a lubricant between the atoms. So here's an example of malleability. I have some Play-Doh here. If I put some compressive force on it, the Play-Doh will bend into different shapes. So I could do that with a piece of aluminum can, right? I can bend it in different shapes. Or the way that this hook was made on this hanger, this hook was bent into shape, and I could bend it out of shape if I wanted to, or bend it back into shape. And you can do that if the metal is thin enough and if it's soft enough. And sometimes if the metal's not soft enough, you might have to heat it up. One of the things that we take advantage of based on the malleability of metals is called the extrusion process. So, for example, I can put this Play-Doh in this, I just took this little scooper and drilled a hole in it. And I'm just going to use this bottle here as a plunger and push that Play-Doh out of that hole. And as it pushes out, you can see that it's coming out and forming a rod. So I just extruded the Play-Doh into a rod shape as I pushed it out there. Here's an example of an extruded piece of aluminum. It was pushed through a metal die or a little cutting shape in the shape of this L, and it formed this aluminum channel. So you could use that because it has a little bit more structural soundness. It doesn't quite bend as easily when you have that particular shape. So we do extrusion a lot with metals, and that takes advantage of the fact that when you push them, they will bend. Ductility is another property of metals. I have some slime here that's malleable, just like the Play-Doh was, but the slime is also ductile. If you pull on it, it stretches. When you pull on something, that's said to have tensile strength, or I'm sorry, tensile force. So I'm putting tensile force, T-E-N-S-I-L-E, tensile force on that, and it stretches out. So let's take a look at what that looks like from the standpoint of the sea of valence electrons. If you hit a hammer down onto a chunk of metal, instead of the positive coming together and repelling, the positive is attracted to the negative, and the negative moves, so the positive can move too and not come directly in contact with that positive. If you stretch it, the particles can all kind of fall into place and stretch out and remain a continuous piece. Now, not all metals are exactly the same in their malleability and ductility. Just like Play-Doh is very malleable, but it's not very ductile. If I pull on it, it doesn't stretch like the slime does. Lead is an example of a metal that's very malleable, but not very ductile. If you pull on it, it doesn't make wires very easily. Here's a wire that's made of steel. It's been pulled into a very thin wire there. Or here's another wire made of steel, made into a paper clip. So it's been pulled into a wire and then bent, so we have both malleability and ductility there. And now let's take a look at electrical conductivity. A little safer this time, we're going to use a multimeter. And I'm going to set this multimeter so that it measures the continuity of the circuit. In other words, if there's a continuous flow of electrons. So I have this probe coming out, this black probe, and then it goes here. And if I touch that to the red probe, which goes back into the multimeter, and this is just powered by a battery, we get continuity. Now there's not very much continuity in my fingers, but there is, because this is only being charged by a battery, there's continuity in the paper clip. There's continuity in the wire. There's continuity, in other words, a continuous flow in the aluminum can, or in the extruded piece of aluminum. So you can see that when the electricity is flowing, the buzzer sounds. So we see conductivity that's happening in all of those metals. And finally, metals can be made to shine. And to demonstrate that, I just want to take a look at a piece of aluminum foil. Now, when aluminum foil is manufactured, one side of it is made to be very shiny. It just comes out that way. And another side is relatively dull. So let's take that dull side of the aluminum foil. We're going to use a little bit of polishing compound. And all I'm going to do is put a little polishing compound on a shop rag here. And then I'm going to use that. It's a slightly abrasive compound. And I'm going to use that to flatten out the microscopic unevenness that exists on that dull piece of aluminum. Now, you can't really see it with your naked eye other than seeing that it's dull. But if we were to look at it very closely under magnification, we could see that, in fact, the surface was uneven on the dull aluminum. So I'm smoothing out that surface right now. So I'm going to go in a few different directions to try to smooth it out nice and evenly. And I'm putting a pretty good amount of force down on that aluminum. And then let's wipe that clean. And you can see that what we have here is some polished aluminum. I'm not sure how well you're picking that up on the camera, but there is a shiny circle there in the center of that aluminum. And that means that we flattened out that surface. So the properties of metals are all governed by the sea of valence electrons. And these are the 4 properties of metals that we've taken a look at. So once again, you should be able to say what the definition of electronegativity is, which have higher electronegativity, metals or nonmetals. Why are ionic compounds brittle? In other words, why don't they bend? Why are they not malleable? Why do ionic compounds have a high melting point? Why do ionic compounds only conduct electricity when they're either dissolved or melted? And you should be able to give an example of an everyday ionic compound. You should be able to list the 4 properties of metals, give an example of how a metal is malleable or how it bends, give an example of how a metal is ductile or how it stretches, Hint, hint. What happens to the dull, rough surface of a metal when it's polished to a shine? Hint, hint. And what theory explains the four properties of metals? All right, good luck.